Hi all, in this video we're going to be exploring the number of ways that we can count or create 6 Pokemon teams such that each type of Pokemon is repeated at most twice. Now, this is a question that I'm personally very interested in investigating because as a kid I've always played Pokemon and I'm still interested in it as an adult. And we all know that beating the Elite Four is one of the easiest things to do, so it gets pretty repetitive at some point, so oftentimes I would like to challenge myself by filling in my Pokemon team with just random Pokemon just to see if I can beat the Elite Four. And so in this case, realistically speaking, if we were to utilize the data that's given to us, there's over 1,000 Pokemon and there's 18 different types. But with that in mind, we also know that Pokemon come in single types and dual types. But what's annoying is that dual types don't exist in every single combination. So for example, like I believe Poison and Steel is not a thing, or maybe it is, but regardless, that's an example. So in order to make this counting question a lot more feasible, what I did was I placed conditions, or in other words, restrictions based on aspects that would make this question a lot harder to solve if I were to use real life data. So here I essentially made a fake Pokemon world such that there are exclusively 6 types of Pokemon and each combination of the dual types were to exist. And so with that in mind, there is a possibility that certain types will not exist, and that makes the problem a lot more difficult to count. So therefore, I'm also putting in this restriction of that each of the 6 types must exist in the team. So in simpler terms, that just means that the Pokemon type exists either once or twice within that 6 Pokemon team. And to make it slightly easier to count, so that way we can fixate on the procedure and the process rather than just the final answer. For each singular type and each dual type, there will be a population of 10 unique Pokemon to choose from. So for example, fire, there will be 10 different fire types. And if I have a fire and flying type, there will be 10 unique fire flying types. And there would be no intersection between the two groups. So that makes it a lot easier to deal with. So in this little project that I did, I utilized partitions of integers, I utilized multisets and combinations, but it's a lot more difficult to deal with when just utilizing these 3 things. So to make it more visual and easier to represent, I utilized some aspects of graph theory. So rather than writing out all the types, I represent each of the 6 types using letters A, B, C, D, and all the way to F. And so because some of the types are allowed to be repeated, because we are using graphs, then what we can use are multiple edges and loops. And so if you're not sure what that is, I will show an example later on, so that way we all are on the same page in regards to what that means. And so with that in mind, with that additional condition that each of the 6 types of Pokemon must exist, each vertex, or in other words, each type, must have some sort of connection, whether it be an edge or a loop that's connected to it. So here are some examples. So this is the graph that I made. So it's color coded, so it's a little easier to see. So each of these labeled vertices, these represent unique types. And so let's say, for example, I have this configuration right here. So if I have 6 Pokemon and 6 types, then what I know must be objectively true is that I have 6 vertices to represent the 6 types, and then I have 6 edges, which includes the loops to represent the 6 Pokemon that I decide to choose, or more specifically, the types that we go with. So in this iteration here, we see an edge that's connecting A and B, so that tells me that I have 1 Pokemon of type AB. And so in this case, because they are dual types, order doesn't matter. So if I wrote this as BA, they're basically the same thing. And so here we see a loop within itself. So loops in the context of my problem is going to represent a repetition, or in other words, an existence of self. So in this case, there's 2 loops. So that means there are 2 Pokemon of type C. D, there's 1 Pokemon of type D. And in this case, this is what I mean by multiple edges, where here we have double dual types. So there are 2 Pokemon of type E, F as such. So in total, we see that there's a total of 6 Pokemon, and that's correlated to the edges. And we also see that there is no repetition in the letters beyond at most twice. So they either exist once or they exist twice. So an invalid example of using this graph or a representation would be something like this. So you can analyze the graph, but if you want to, you can pause the video and test it yourself. That's the teacher in me, I guess. LOL. I hope no one watches this video. I'm kidding. Okay. All right. So if we were to go in alphabetical order, here we see A has a loop within itself. Hence, we have the first Pokemon of type A. And then here we see an edge connecting A and B, thus giving us type AB. And so if we follow the iteration, this thus gives us BD, BF, CD, and E. So this does secure the 6 Pokemon. Even though these are loops, we still consider them to be edges. So we have 1, 2, 3, 4, 5, 6. So 6 Pokemon, but the problem is right here. This violated the condition that was initially stated such that a type can be repeated at most twice. And we see that visually speaking here as well. So we could do this visually, but since we're in a combinatorics class, we might as well use numbers to represent what's going on as well. So in conjunction with the visual aspect that we see here, what I did was to organize the information a little bit more. Let's denote or make some definitions. So given the conditions, there only exist 5 cases or 5 possible vertices. Well, we have a vertex with 1 edge coming out of it as such. Oh, whoops. Something like this. Or we have a vertex with 2 edges. So something like this that's connected as such. So this would be of degree 2. And a loop, if we follow traditional graph theory rules, a loop, although it is one singular entity, we count that as degree 2. And there's a possibility where we have a vertex with 1 loop and 1 edge, and that's degree 3, the 2 plus 1. And then we have a vertex with 2 loops. So these are the only 4 possibilities. And again, the maximum is 2 loops because we have at most 2 types and the minimum is 1 type. So it's either 1 or 2. And so here we can develop a system of equations such that if these represents the values or the amount of vertices with these aspects, we know for sure that in total we must have 6 vertices. And if we apply the degrees to each of them, their respective degrees, so for example, E sub 2 is of degree 2. So if we multiply that by how many of these vertices there are, then that gives us the total number of degrees that it contributes to the overall graph. So in total, we have a degree 12 for every single scenario. So all valid graphs that satisfy these conditions that were given in the beginning of the problem, they must satisfy the condition that there are 6 vertices and the total graph has a degree of 12. And so if we utilize some algebraic manipulations, I'm not going to show that because that took me a while to do, but these were some findings that I have found. And so with this in mind, what this helps us do is that this allows us to put limitations on different cases. Now, what does that even mean? So what I did from here was, well, because we know for sure that this is a degree of 12, and we need 6 values to give us a degree of 12, we can view this as a partitioning question such that we're partitioning the number 12 into 6 parts, utilizing only integers 1, 2, 3, and 4. And so again, if we're talking about partitioning, we don't really care about the order. It's just about making sure that it sums to 12. And so in this case, the sum or the sum ends, each part of the addition represents a degree of each of the vertices. And so to avoid overcounting and ensuring that every single graph that we have is disjoint and not overlapping, we're going to condition on how many of each type of vertices exist. So for example, this right here, I listed out all possible partitions of 12 into 6 parts using 1, 2, 3, and 4. And so although this is a nice way to organize or separate this entire problem into cases, it's not immediately clear as to what these 2's are, because this degree of 2 could represent 2 edges or it could represent 1 loop. So what I did here was I took every single one of these partitions of 12 and I translated it into rather kind of like, well, you can kind of think about it as a multi-set. originally. But here I'm counting the total number of ones, the total number of twos, the total number of threes, so on and so forth. And so again, this is not that great. It does help break down the overall problem into cases, but let's be a little bit more specific. So utilizing this, I developed even something more specific. So I copy and pasted this right here. And so you can see that we have, again, our 5 types of vertices: E sub 1, E sub 2, L sub 1, EL, and then L sub 2. And here are their respective degrees. So again, what we know for sure is that there's a total of 6 vertices. And if we were to substitute in those values or the quantity and apply the degree, that should give us a total degree of 12. Okay, so from here, I listed out all the possibilities. And from here, I condition on what each graph looks like. So for example, case 1, we have E sub 2, which means that we have 6 vertices of degree 2 with only edges. And so with each of these cases, I would draw out a sample of what one case would look like, and then think about how I would go about counting that. So, I mean, you're welcome to pause the video and like slowly look through it, but for the sake of time, I'm just going to scroll through that. So what this does for us is that we're only counting the different iterations of the graphs, not necessarily how to choose the Pokemon to represent each type of these teams. So in order to get the final answer though, what we have to do is we have to multiply each number of ways to pick Pokemon types, either single or dual types, and then we multiply by how many Pokemon of each type or each quote-unquote category that exists. So I don't know about you, but I'm not trying to multiply that out because I believe that what's most important here is the algorithm or how we approach this problem. And so this problem is extremely large. It's very difficult to count. Hopefully I did it right, but if you have any critiques or any suggestions of how else I can count this, that would be welcome. But if I were to do this again with more time, I would definitely want to look into how I can simplify this procedure. So rather than breaking it down with cases, I would rather develop some sort of algorithm that can generate it for me, or even utilize ideas of generating functions. Because there are aspects of generating functions within this problem since we are, I just lost my train of thought. But there are aspects of generating functions in here that I would like to explore. And also, what would the problem look like if the populations were not of all even size? What if they were all different? And what if certain intersections or combinations did not exist? So that ends my presentation, and please let me know if you have any suggestions of how I can improve this, and I hope you enjoyed. Bye!